recorded. Okay, good. So if there are any questions, just type them in. Otherwise, we'll just get going here. The one thing one announcement I do want to make, though, is that the first recitation is going to be posted this afternoon. Okay, so right after lecture, that's going to get posted. Okay, so let's see here. So today, and I'm assuming people can see the screen share. Okay, so today we're going to start very much at the beginning. The relational databases are based on a formalism, which essentially is called, well, it has two components. It has the relational algebra and the tuple calculus. So what we start out with here is just kind of like the mathematical underpinnings of relational databases. As we see, this will change a bit to make it more practical. So there's a lot of practicalities that we'll enter in. But in the beginning, we'll just start out with kind of more of a simpler, purer case. Okay, so. All right, so this is what I would basically say is the ideal picture. This is the picture of how relational databases are supposed to work. So in the ideal picture, what we have is at the very top, we have some kind of declarative expression of what the user wants. Okay, so in fact, we can make this even more ideal, and we could put natural language at the very top. So I could, there's a database somewhere, and I could say, give me the students who scored more than a 5 in the database course. I'm sorry, give me the students who scored 5 in the database course. I could say something like, give me the students who scored 5 in the database course who don't have, on the exam, who scored 5 on the exam, who don't have all of their labs cleared yet, okay? So what that is, again, that's just like kind of a statement of what you want. That's a declaration of the answers you want. I'm doing it in natural language, but then there's a corresponding way we can, this whole issue actually of mapping the natural language to some kind of logical statement. In fact, actually, that's my research area. I work in that area. But what we do in the course here in the database course is we basically see it as some kind of logical expression as to what people want, what you want as an answer to your question. All right. So that's the tuple calculus, and we're going to cover that today. Those are expressions that achieve that. Now, the thing is that those expressions aren't very good for a computer. A computer can't just take like some expression, some declaration, a declarative expression of what the user wants. Computers can't work with something like that. They need something that's procedural. They need something that they can actually execute, right? So what that is basically is that's the relational algebra. So there's a correspondence between these declaration statements, these statements in the tuple calculus, and this what we're going to call the relational algebra, which is the first thing we're going to cover today, which actually gives a procedure for a computer to actually obtain the answers, okay? And the interesting thing mathematically is that the tuple calculus and the relational algebra are representationally equivalent. They express this. Any question you can express in the tuple calculus, you can render in the relational algebra. Anything you can render in the relational algebra, you can express in the tuple calculus. They're equivalent languages, or we have equivalent expressive power. So that's kind of like the core kind of mathematical basis of all of relational databases. And for this observation, or this discovery, you might say, Ted Codd, who was the originator of the relational model, won the Turing Prize. That's the highest prize you can get in computer science. Okay, so it was a good result. Okay, so another thing that comes in with databases, though, is that there are a whole set of equivalent relational algebra expressions. All right, they all do the same thing, but some do it much more efficiently. Okay, so the translation then, once you get to relational algebra, to more optimized relational algebra, is another aspect. That's basically the heart of what's called query optimization. All right, so this is the ideal picture. Okay, and I'll keep on looking in the chat if anybody has any questions they want to get any clarifications. All right, so here's an example. So in that natural language, you might have something like, give me the names of the companies in Sweden that have a supplier from China. Okay, so there's kind of an assumption here that we have this database down here that has a table of company, with an ID and a name, and then a country, and then a revenue, how much revenue the company generates, and then supply. So this right here determines a graph. So basically, this can determine, say for instance, we have an ID number 1. The name of the company might be Volvo, and then there might be a Chinese component supplier, and that would be another company here. And then this right here represent basically that component supplier is supplying Volvo. Okay. This will be much more clear. I mean, you'll see how you can represent these things. But what we have here then is we have the names of the companies in Sweden that have a supplier from China. Okay, so this right here is the actual equivalent tuple calculus statement. Okay, so what this is basically saying, it's not really like logic. It's like a syntactic sugar over logic. So this should be like a backwards E right here for the exist quantifier. But what we have here is basically give us the names of a company X. This dot notation basically says, okay, pluck out the name of it, and then the country of it should equal Sweden, and then there has to exist a supply, so there has to exist a company that's doing the supplying, where that country is from China. And what we'll see here, you'll get pretty good at this. These are the join conditions that allow for everything to kind of work together. All right, now students have a tendency to have a harder time with the tuple calculus than they do with relational algebra. So it'll get easier once we go to relational algebra. You'll see this in a second. Okay, so first of all, let's just talk about abstractly what is an algebra, because I mean that's the thing. We're gonna be covering this thing called relational algebra, and what mathematically what is an algebra? So what an algebra is, it's basically a set of operands. Okay, so these are things that you can work over. So in the classic algebra, this could be like the real numbers or something, right? And then the operators are things that you ways that you combine operands and yield operands. And that's the key issue right there, is that algebras are closed in the sense that you have a set of objects in the universe for the algebra, and then you have operands like plus, minus, division, multiplication. So these are the classic ones in arithmetic. And then you have the operands, which could be variables in the algebra case, the classic algebra case, or values like 17. But the idea then is if you take two operands, you take 17 plus 2, you get another operand which equals 19. Okay, so they stay closed. So now when we think about this, we're going to be talking about the relational algebra, right? So what are the operands in the relational algebra? And that should be no big surprise. The operands are relations. So everything's going over a set of relations. That's why it's called the relational algebra. So we're going to have operands. They're going to take two relations and then yield another relation. That's what they do, right? That's what they do. And this basically will wind up being something procedural. Now, at this point, what I'm going to do is I'm going to go over here to the scribble board here, because I think it'll be better just to kind of do it that way. So I'll stop this share, and then I'll share screen. I was trying to do this. Great. I was trying to do this by moving screens, but I find that it's more easy just to do it this way. Okay. So we're going to be doing the relational algebra here. All right. So first of all, what's a relation? Okay. So a relation is, say, R. R can be a relation. So R is going to equal something like this: A, B, and C. So those are those are like the header of the table. It's like a table, right? You guys can all see this, right? That A was a little bit weak, though. Yeah, there it is. A little bit better A. I'm assuming, yeah, good. Okay, so that's basically it's a table. This is an empty relation right now, but let me just give it some values. A1, B1, and C1. Right? So I'm going to keep it abstract. This could very easily be the thing with companies, right? It could be like a company name of well, it could be an ID. A could be ID. And that could wind up being 1 or something. And then B could be like name, and that could be IBM or something. But we're just going to keep it abstract here with just using these symbols here. Okay, so let me just kind of add some more ones in here. A1, B2. All right, that kind of sucks. Okay, let's see here. Undo. Undo, yeah. 2 and C1. Okay, that's fine. So that's another relation right there. Okay, so this is the relation then consists of the set of attributes A, B, and C, and then the set of tuples. So there's two tuples here, right? There's one tuple that's A1, B1, C1, and there's another one's A1, B2, C1, right? Okay, so we have two tuples there. Now, what are some operands? Okay, so what are the so those are the operands, our relations, right? And let's start out with basically what we're going to talk about the relational algebra as a set of operators rather. So the operators, this is not so great, equals. All right, so the very first one we're going to talk about is one that is called projection. That really looks bad. Let's see if I can do this with two hands. Control Z, Z. Okay. So projection is the pi symbol. Okay. Then the next one we're going to do after that is we're going to do one that's called selection, which is the sigma. Oh, that's a little bit better. Okay. Then we're going to talk about one that is union. All right, there's a U for union. And then we're going to talk about one that's called, this is the harder one for people, it's called Cartesian product. So this is that's like a big X. It's an operator. Okay. And we're then going to also talk about something called renaming. Okay. There's some other ones too. There's set difference, and there's intersection. Okay. But that's it. That's pretty much it right there. Let's see. Is that it? Yeah, this is the core relational algebra right here. All right. Now, in truth, you don't need, let's see if I can get rid of this. Control Z. Good. In truth, if you have a union and you have set difference, then you can actually derive intersection. Okay. So these operators right here, these kind of core operators here are really the true core relational algebra. Okay. Does that make, okay, so that's just kind of introduction. We're going to go over, what we're going to do now is we're going to go over each of these operators and kind of show what they do, what they mean. Okay, and these are all on the slides, so you know, maybe actually it's not a bad idea for people to actually have the slides and to look and to follow those along as I'm doing this. But I'd like to actually do it on the scribble board here. All right, so just a couple more points here. The projection operator, that guy right there, which is a pi symbol, that guy takes only, it's a unary operator. So it only takes one relation in, and then what is it? I mean, it's a relational algebra here, right? So it's an operator. So it takes, this one is unary. It takes one relation in, and then what does it give out as a type of thing? It gives out a relation, okay? The selection, that also is just a unary operator. So what it does, and what we're showing, you know, there are a little bit more arguments to these operators, but I don't dare kind of write that in there at this point because it's already too fiddly. This also is a unary operator, right? It takes in one relation, and then it does something to it, and then yields back another relation. Union, however, is a binary operator. It takes in two relations and then gives you out a single relation result. Same with the Cartesian product. That gives you takes in two relations and gives you out a single relation as a result. The renaming is unary. It gives in one relation, takes out another relation. And then the minus operator is binary. It takes in two relations and then gives you out one relation as a result. So let's go and let's define these things here. Okay, so control, let me just delete everything. Very good. All right, so let's do projection first. Okay, so let's say we have R equals, So what I'm going to do here is I'm just going to do this right here. This is going to be a kind of a common way you see this. Okay, so R is a relation, it's a table, right? That has its own name, it's called R, and it has the attributes A, B, and C. Okay, and then the state of this table might be something like, let's just say A1, B1, C1, and A2. B1 and C1. Okay. Yeah. So if we say basically project, so it's a big pi, and then what we put down here is a set of attributes, or a sequence of attributes, but it doesn't, in this case here, it's a sequence of attributes. So you could actually have repeats. So what about this right here? So if I say that I'm doing it over R. Okay, so here we see the state of R has two tuples, and we're doing a projection of A over R. So all this does, it's really simple. All this does is it's just going to bring, it's going to basically equal, or it's going to, this is going to yield the relation A1, A2, A. Okay, so all the projection does is whatever you name as the attributes, it simply goes to those and it projects those out. All right, is that, I'm assuming that that's fairly clear to people. Okay, so what happens though if we do the following? Let's see, I'll just do it this way. Actually, let me bring in the mousey here. Do this with two hands. Sorry, I'm still kind of getting my coordination done here. Okay. I mean, I should be able to select, but it's a little hard for me. I mean, in other words, I should be able to kind of go in there and then not have to redo all this, but okay, I'm still getting it worked out. Okay, so now what happens here if I project on B here, the attribute B? Okay, what should that equal? Well, it's going to be, a relation is going to come back with B as the attribute, and then it's going to have B1 and B1. Okay, well, yeah, good. So very good question. So there's a question here that exactly is this. So the question is, do we get this B1, B1, or do we get what might seem to be more natural? Do we just get that, just B1? So this comes down to basically the question of, is the semantics based on sets or is it based on bags? Okay, bags doesn't sound very mathematical, I know, but BAGS, bags, okay? Because the bags allows for repeats. So that basically comes down to the question of set semantics versus bag semantics. Okay, so when we talk about the core kind of relational algebra, the idealized picture, we're actually dealing with set semantics. So the answer here was just one B1 just not being repeated. That's the answer here in the idealized case. So when I say that the semantics, we're doing the idealized case, we're dealing with set semantics, then we only get back B1 here, just one tuple, okay? Because we don't allow for any repeats. All right. So we're going to stick right now with set semantics, but we'll have quite a bit more to say about bag semantics later. Okay, so let's go back here. And then let's just kind of generalize that a little bit by saying, what if we say, oops, B and C here, and we're going to do that over R. Okay, if we do that, then what do we get back as a result? We get back the result B1, C1, B, and C. Okay, and the reason, of course, is because we're dealing with the set semantics, because B1, C1 repeats, right? So it would be 1. So under set semantics, we get that back. I hope that's clear. Okay, so projection is really, that should be pretty straightforward for people, I hope. Now let's talk about selection. All right, hopefully this will work. All right, so another unary operator is what's called selection, and that's this big sigma. Big sigma. Big sigma. It's not very pretty, but anyways, you get the idea. Okay, so now what sigma does, the select operator, what it does is it takes conditions here. So A equals B, I'm sorry, well, that could do that, but A equals A2. Okay, and we can apply that over R. All right, well, I hope that yeah, anyways. So what this does then, this is a little bit different. This, instead of like doing projections, instead of kind of going and like basically doing projecting out an attribute, what it does, it's basically going to do evaluation across here, and it will find the tuples that the condition is true for. So A, the attribute A equals A2. That's not true here, but it is true here. So the result is going to be A2, B1, C1. Okay. And then, of course, we have I could write A, B, C here, but I'll just keep it like that. Okay, so that's the selection operator, and that's all fine and good. So let's just combine these two together here. So I hope that, do people understand that? Is that any questions about that selection? Okay, I don't see any questions. Yeah, this should be pretty straightforward. What about this? What about doing the following? What about saying project A from, good, select B, B equals B1. What does that equal? So the internal part here, oh, sorry, that doesn't equal anything. You could, so someone would say, well, that, I mean, it's not even defined. So now that's better, right? It's because now we're actually applying it over a relation. So the very first operator, what we do here is we apply the select operator over R, and we look for the tuples where, you know, B equals B1. Oh, that's both of them. So what this returns here, this returns a relation. This internal expression here returns a relation, and it's just this original relation because they both have B1, B equals B1 for both of those. And then it projects out A. So the answer, the full answer of this is going to be A1 A1, A2. All right, so now you can see here that if we did the following, if B was corresponding, let's say, to country, and then A was corresponding to company name, we could say something like, give me select first the country equals to Sweden, and then project out the company name. And that will give us all the company names in Sweden, right? So that's how it would correspond to a real table. That's something, you know, a real example. All right, so that should be hopefully fairly clear. So let's go on now, and let's go on to the next operator. And the next operator we're going to deal with is union. Okay, so now I'm going to basically say this. I'm going to say that S, so I'm going to bring in another table here, S, A, B, C, all right? And then what I'm going to say is I'm going to say that that has a value A2, B1, and C0, okay? So so we have two relations here, and then the question is, what is R union S? What does that equal to? All right, so this is really straightforward, right? So what we have here is it's going to basically be three tuples. It's going to be A1, B1, C1, A2, B1, C2, C1, and A2, B1, C0, right? So it's just going to be all these union together. That should be really clear. All right, let's do this. Let's say this. What about this? A1, B1, C1. Okay, so when we union these two together and we're under a set semantics, then that we have a repeat tuple here. We have this A1, B1, C1, so we're only going to get 3 tuples in the result, right? Good. Okay, so that should make sense, I hope. So what about if we now say, let's just so union is let's just cover while we're at union. Why don't we do why don't we get the other ones too? That doesn't matter. All right. So what is Rn intersect? Okay, right there. What's that going to equal? All right, that's going to equal a relation over ABC. ABC. All right, it's going to equal a relation over ABC that's empty, right? It's just going to be an empty, so there's going to be no tuple there, right? Because there's no tuples that are shared between, and if there were, it would show up there. Then let's see here. So then, what about minus? That's also going to be fairly straightforward. So we're going to cover all these basic set operations right here. Oops, that was weird. Okay, minus S. All right, so what is that going to equal? That's going to equal R, right? That's just going to equal R, because there is no shared tuple here. So basically, if you minus this out, you basically walk through this one and say it'll survive if it's not there, and then nothing is there. So, but if however I had A1, B1, and C1, then this would disappear. So the result of this would just be the single tuple A2, B1, C1, right? I mean, this is really should be pretty straightforward for everybody. All right, is there anything more to say about this? Yeah, there is. That is the following. What is the all right, now we have this guy. Okay, what is R minus S, or R intersect S, or R union S, or R, well, say intersect minus, set difference, or union. So the thing is that for this to be a legal operation, the two relations are said to must be union compatible. All right, and what union compatible means is they have the same set of attributes, or what I would call the same signature. So we have, this one has A, B, C, this one just has A, B, all right? Therefore, it makes no sense. Basically, what this equals is undefined, okay? So if later on you're going to be writing these expressions and you happen to kind of do set operations where the signatures aren't equal, then you're going to wind up crashing the system, as it were. All right. Now, the thing is, we're not going to be so super serious about this in the following sense. So if we have generally speaking, what you allow for situations like this. So they don't have to have the exact same name. Now, when we do the mathematical, and basically what we're meaning by union compatible is basically that they have the same cardinality. They have the same, the same n-array. Basically, it's the same number of basically the same number of columns. Okay, since we're not really talking about types yet or anything like that. So so this actually, so generally speaking, I'm not going to ask you to do renamings to get everything aligned. We'll come to that renamings later. Basically, what we have here is we can allow for this because at least they have the same number of attributes, right? So at least it kind of makes sense at a certain level. So generally speaking, we kind of allow for that kind of at least flexibility when it comes to union compatibility. It's called union compatibility, but it could also be called difference compatibility or intersection compatibility. But you refer to it as union compatibility. Okay, hope that's clear. All right. Actually, I think that's here. Boink, boink. There we are. Okay, so now let's get to something else here. All right, so I'm going to say A1. Uh-oh, that sucks. Get back. Can I undo from that? No. How did I do that? Maybe my little thingamabob pointed down there, and then maybe I was like around there somehow, and I clicked on it. Anyways, all right, enough excitement. In fact, I'm going to change this right here to instead of B, I want to call it something else. Oh, different color. Okay, I'm going to call this E. I just want to make sure that these are different attribute names. So there's no B there. Okay, so there's E1, A2, E3. Yeah, okay. So now we get to the following. This is usually one that students will have a little bit more difficulty with, but we're getting close to finishing up the relational algebra here. So we get to this this Cartesian product operation. So the Cartesian product operation, what that basically says is it says we're just going to create. So for instance, so when we do this right here, so I say R cross S. Okay, R Cartesian product cross S. What that's going to equal is that's going to equal something that basically it's going to equal a relation that has A, B, C. Okay, now I'll call this A prime just because it's coming, from here, and then E. Okay, I just put the prime in there because we'll have a repeat of the of A otherwise. I mean, I could just change the name to prime here. Let me do that. Okay. All right, so this will give us a relation that basically has those attributes here. So what it's going to wind up doing, there are going to be 4 of them. E3 or E2. It doesn't really matter. It's E3. It's a pretty grubby 3. But looks like actually EB. And let's see if I can get to that thing. That even makes it worse. Anyways. Yeah. So the technology is not perfect here. Or maybe it's an operator of the technology is not perfect. All right, so what this is going to give us is it's going to give us, basically, it's very simple. I mean, it's just going to do the following blind thing. It's going to take this tuple, and then it's going to basically match it with that tuple. It's going to take this tuple, and it's going to match it with that tuple. It's going to take this tuple, match it with that tuple. It's going to take this tuple, and match it with that tuple. So therefore, we're going to get 4 tuples. I don't want to write all this out. This is going to be kind of a pain. Maybe if I do the following, I'm going to get rid of this. Okay, so that was a deletion of that tuple. So what we're going to basically here now is it's going to match this one with this one, this one with this one. So we're going to get 2 tuples as a result. So basically we're going to get A1, B1, C1 matched with A1, E1. And then we're going to get A2, B1, C1, A1, E1. Okay? So if you have N, let's say I have N tuples here, and I have M tuples there. So there are 2 in this case, and there's 1 in this case. How many tuples are going to be in the Cartesian product? How many tuples are going to be in the Cartesian product? Well, it's just for the following: N times M. So that's the size of it. Yeah, good. So it looks like a lot of you guys got that right. Okay, so that's good. Yeah, so it's all pretty straightforward, in fact. And let's see, are we basically done with the relational algebra? Not quite yet, but we're getting there. Let's go right. Let's maybe go back to the. I don't want to do the. Let's see here. We're just gonna kind of quickly go back to a different share screen. Okay, I think I can basically say new share, but I'm going to say stop share. And then I'm going to say share screen. And then I'm going to click on that. Good. Okay. So this is just kind of what we basically talked about this. This is just kind of a recap of that. There it is in kind of, there's your selection operator. There it is in the pretty right font there. Projection, product. That was the product. That was, so here's an example of product right here where we have R1 and R2, and then we do the product here, and then we get all the. So as you see here, since B is repeated here, it gets a new name here, because if you don't want to have situations where you're having the same name repeating. that kind of makes it poorly defined as well. Okay, theta joins. So what we had here is we have what are basically is called some syntactic sugar here. I want to get to this right here before we do this, though. This is basically what's called a renaming operation. So it's this row operator, and what you do is you can give up a brand new renaming to the relation. So, for instance, this would be something where we could do here's an example of renaming where we have a relation R here, which is basically is the bar and we have the name here. So we have bars right here. We have this underlying table here called bars, and we have the name and the address. But let's say we want to change the name here to just basically the bar. We want to change the name to bar. Then there's several different ways of doing that. This right here is kind of the one that's kind of in the notation I was developing before. So actually, let me just go back here and just do that in the. It's too bad I can't do split screen. That would be nice. Actually, maybe I can. What am I thinking here? Sorry, guys. I mean, I'm kind of a little bit stupid. I mean, these things occur to me later. I'm going to do it this way. Or? Yeah. Maybe? Yeah. Why didn't I think of this earlier? So if I share a screen now. One sec. There we go. It still might kind of not be so great, but now I can at least move things over and have a little bit better chance. All right. Okay. So what we had here is we have like the idea then of doing renamings here. So let me just go right here. Let me do a select all, control all, and then let me delete that. Okay. So what we have here is what I want to show is basically this. If I have R, and it's basically A and B, okay, but I would rather have it R being that B turn into a C. What I can wind up doing is I can wind up saying this. I can say rename, and then if we look at the syntax here, oops. This row operator, what does it takes basically, you just put in a full signature here. So what this renaming is going to wind up doing, if I say basically, I want it to be S, let's see, I said A, and I said I want it to C. That's going to then be, and I do that over R. Okay, so I did the renaming, that's the row operator, and I basically am giving it a fresh signature, right, where I have the S, A, C. What that's going to wind up giving us, whatever the contents is here, it's just going to copy the full relation, and it's going to now be called, now it's going to have the signature of S, A, C. And this, whatever this is going to be equivalent to whatever that is. This is going to be equivalent to that. Okay, so another thing I wanted to show you guys, because it's kind of, there are kind of two ways in which you can specify things. And this will come in handy when it comes to the to doing your assignments. Okay, let me delete that. There's two different ways you can do this. You can basically do it as a program, which I think a lot of students like to do. That is what you would say, is you'd say something like this. I could say, all right, first of all, give me the R equals project A, B from S. And then T, that's another relation, equals R union V. Okay, V is another relation. All right, so what it's doing right here, if you want to kind of make it more kind of programmatic, what it's doing here is we're basically doing this operation. We're doing this as a program, as a relational algebra program. All right, so the first thing we're doing is we're calculating the relation R by basically going here and projecting out A and B of S. And now we're going to calculate the relation T with R union V. Okay, so this R here winds up being union with V. All right, so let's see, there's a question here. Should there be duplicates in the result, assuming set notation? Actually, by definition, if you do a Cartesian product and they're both sets, the way we specified it, you won't have any repeats to worry about. But again, everything always comes down to, like, if you want to think of it differently, you could say every time you do operations, if it's under set semantics, you remove duplicates. Okay, that's all. So that's just kind of the rules that are being kind of applied in the background in terms of what gets yielded. All right. So anyways, but getting back to this right here, you can write things as a program, or you can write things in the following way, and that is like this: T equals, you can make it as kind of one big, expression, A, B, S, union V. You see that? So we're not calculating. In this case here, we're doing everything in line. All right. In the second case, we're doing everything in line. In the first case, we're doing it kind of more as a program. All right. So those are the two different ways you can write stuff. And when you do things in line, when you do like in line like this, you can then also do stuff where you can give it like new signature. So you don't have the renaming. You don't need to have the naming operator. I could say something like C, B. Let's see here. Let me just do. I could say, instead of this right here, I could say R, C, B equals, and then I'll script. And then this AB here. So the idea here is that AB here, the renaming is being achieved just by how you specify it in the program. So if you do things as kind of like a program, then you don't need to have a renaming operator. But if you do things like this, then you will, in fact, actually need to have a renaming operator. Okay, so I hope that's clear to people. Right. It'll be all right. So let's see here. So what I want to do now is we want to get to something. Okay. So anyways, let's just kind of round this out here. What we've achieved here. So what we've achieved here is la-di-da, control everything, delete. What we've achieved here is we've achieved basically the definition of the relational algebra with the operators pi for projection, sigma for selection, union, difference, okay, renaming, and Cartesian product. Okay, so these right here form the complete relational algebra. So everything I show you from here on out can be basically simulated using these operations. Okay, so mathematically, there's nothing new. I'm not going to show anything new in the relational algebra in what follows. It's just what follows here is what's called syntactic sugar to make things easier to work with. All right. So given that, let's just go on to the first one. And that is what is called, let's see here, product we've done. Okay, so what's called a theta join. So what a theta join is instead of doing the Cartesian product with an X, it does a little bow tie, and then it has a condition on that. So what basically the Cartesian product is doing, what the theta join is doing is it's doing a Cartesian product followed by a selection. All right. So here's an example of a theta join. So it's a little bit easier to write than the Cartesian product plus the selection. So basically what we have here is we have bars, beers, and prices, and then we have bars. Okay, so what we do here is when we basically say we want bar info, and that basically what bar info is going to mean here is basically, well, it's going to be the bar, and then inside the bar it's going to have the beer and the price for that beer, and of course the name of the bar and the address of the bar. So to build up a table like this, you could do this with how would we do this right here with just the elementary, so we have cells, bar, beer, price, and okay, so we have all that. So basically, how do we do that just using kind of the elementary operations? So let's see, I just got to jot this down on the side. I got cells, bar, beer, price, and I have bars, which basically have a name and an address. All right, so if you do the following, if you basically say, Control A, no, Control A, and then delete. If I say the following, I basically say, all right, I'm going to take cells, and I'm going to do a Cartesian product with bars. And then I'm going to do a select where the, okay, so now when I do cells and bars as a, okay, how many tuples, okay, just bear with me here. Cells cross bars there. All right, so if we go back here, we have 1, 2, 3, 4, and 1, 2. So we have, so in the Cartesian product between cells and bars, how many tuples are there? 8. Very good. All right, but look, there's only 4 tuples here, right? Okay, because only, now we have 8 tuples that come out. So we have, like, for instance, we have Joe's bud matched with this tuple. We have Joe's bud matched with that tuple. But notice here, when we match Joe's bud with that tuple, it doesn't really make much sense because this is Joe's bar and this is Sue's bar, okay? So what we wind up doing here, back to here, if we basically say this, we say select, and then I say bar equals name, then what that's going to do is it's going to go through all of those 8 tuples, and it's only going to retain those where the bar equals the name. Okay, so the name here equals the bar here. So the top, as you can see, there's going to be 8 tuples, but Joe's matched with Sue's here is not going to make it into the result because the bar Joe's does not equal the name Sue's, right? But when I join here, Joe's with Joe's here, it's going to make it into the result because those are equal. All right. So that's the whole notion of joins. Okay. That's why it's called a theta join. It's because you're joining on this attribute. You're basically selecting an attribute here, bar, and you're selecting an attribute here, name. And so you're doing a Cartesian product followed by a select, which makes sure that those are going to match. All right. So that's basically what a join is. So you're going to get good at that. So instead of writing all this out every time, what you do instead is you just have a theta join here. Okay. All right. I think this is a good time for us to take a little bit of a break. So why don't we come back at 11:15? All right. So okay. There was a comment there. All right. So let's just come back at 11:15, and then we'll finish this up. And then, of course, obviously, this is going to be kind of what your recitation is going to be about. So that you're going to get a bunch of problems that are going to get released that you can kind of work with. Okay, so let's reconvene at 11:15. Okay, I assume everybody can hear me. Did anybody? So a question came up here during break. Did anybody get the email from support that gives you a PostgreSQL database? Okay, good. So a lot of people got it. So okay, so those who didn't get it, maybe send an email to support. It might be the best thing. So that's going to be support@cs.umu.se. But I mean, I'll look into it. I mean, the thing is, one thing I wanted to say about that, just to kind of, this is kind of an aside. I actually would prefer it if you guys downloaded your own database. And I mean, well, I mean, how many of you guys use Windows? on your laptop machines? Okay. Does anybody use Linux? I hope. Sadly, yes. Yeah. Okay. I mean, the thing is that let's just be frank about it. I mean, when you run databases or database servers, you're running them on Linux. I mean, I don't know what percent run on Linux on the internet, but I would say more than 95%. I mean, good grief. I mean, if you're gonna run like a real website on the internet, which is what usually you're gonna do with a database, you're going to run it under Linux. So yeah, maybe it's best if you do have Linux on your own machine, I would recommend that you install PostgreSQL because it's good practice. I mean, it'll definitely come in handy. If you have a Windows box, I just use the one from support. Or you can install PostgreSQL on Windows as well if you wish. But in general, it's not that hard to install your own database. And I think it's good for students to do it because it gives you kind of more command. You shouldn't really depend on others. I'm sorry, that sounds terrible. I mean, you should be able to kind of do stuff yourself. I think I would advise that because you don't want to be kind of waiting for people to kind of do administration for you. It's a better attitude just to kind of just get in there and do it yourself. Get your own laptop, get super user on the laptop, and go to town. That's my advice. But anyways, that aside, yeah, if I'm neutral. I mean, it doesn't matter in terms of the labs which one you use. But I mean, the thing is that yeah. Anyways, I won't even get into it. So let's just continue on here, unless there are any other questions related to other stuff. Okay, so let's get back to here. Okay, so we just did theta join, and that's, as you can see. I mean, as I showed, and it's still there. It's equivalent to these base operations. So there's another one that's kind of becomes very much in use, very very useful. It's even more syntactic sugar. It's called a natural join. And it's just you take two relations and then you just bow tie them together. All right, there's this right here, R1 natural join. It's just a bow tie. It looks a lot like a theta join, but there's no condition on it. And what the conditions that do hold on it are basically about when attributes are named the same. So what we have here at natural join, when we have bar here, and then we have notice how they're both named bar. So we have two attributes here in the natural join between cells and bar. We have an attribute here and an attribute here, which are the same name. Okay. And when you do natural join, what the implication is that attributes with the same name have to equal each other on the join. And then since they're just duplicated names, you can project out one of the names. All right. So basically what this leaves us with then is that the attribute bar is not repeated as it would be in a theta join. Okay. So it's a convenient way of doing things. And so what it does though is it's a good practice actually, because what it does is it makes it so that you're having lots of attributes with the same name across tables. All right. So when you look at kind of good designs, in industry and stuff, I mean, when they do this, it's kind of nice actually, because it makes querying a lot easier. All right. So it's kind of it's not always the case, but anyways, a lot of times it can be a good convention to follow. All right. So as you notice, I mean, clearly you can simulate the same thing with a specific set of base relational algebra expressions, projections, and selections in a Cartesian product. All right. Okay, so that's natural join. That'll come in handy. All right, renaming, we did that already. Now we get to division. Okay, so division, this is where I think things get a little bit more complicated for students a lot of times. The division operator, first of all, the division operator is not elementary. So you can define the division operator with the basic operations in the relational algebra. All right, so it's nothing new. And I mean, it's not adding any power to the language, but it is kind of semantically, it's allowing us to do for all type queries, and I'll show that in a second. Now, the correspondence it has to division in arithmetic is kind of loose, so don't think too much about your kind of don't think too much about standard notions of division as we define this thing. All right. So basically, what division does. Let's see if I have a good example here. So basically, what division is going to do here is it's going to basically say. I mean, I'll just ask you guys straight up. We have a cells relation here where we have a bar and they're selling a beer, right? We have Joe's and we have Sue's bar. And then we have all the beers, all right? So all the beers are Bud and Miller, all right? It's not a very interesting world in terms of beer drinking, but this is the world which is defined in this database. Now, I'm asking, so just which bar serves all the beers? All right. So that's another way of saying that. Give me all the bars for which there does not exist a beer for which they do not serve it. Does that make sense? I mean, are the two? I just want to get you kind of used to thinking this way. Are the bars that serve all the beers, are they equivalent to the bars for which there does not exist a beer for which they do not serve it? Is that? I mean, are those equivalent? Yeah. Okay. So you got to think in terms of like yeah, they are logically equivalent. Okay. So but it's good to kind of start kind of thinking this way a little bit, because sometimes those renamings, or those, I'm sorry, not renamings, but those rephrasings are going to help you a lot in terms of kind of figuring these things out. All right. So what we're after here then is we're after the bars that sell all the beers. All right. So what we have here then is about, we're going to have bar all beer. So basically we have this this division operator. Okay. So now the division operator just, it said it will compute this. So basically what a division operator will do is it'll take one relation in, another relation in. Now the relation that it takes in here is always going to have a subset of the attributes of the relation coming in. This relation here. And what it's going to do is it's going to basically just compute the set of let's see if I can do this right here. All right. Control A and then delete. All right, so let's just make it a little bit more abstract here. So basically, if we have this, we have R, and that's going to be over X. Okay, so X is a set of attributes. So when you see X and Y and Z, I'll be using those as sets of attributes. Okay, if we say, for this to make sense, basically we have to say that Y is a proper subset, undo, of X. Okay, so this in this example we were doing before, the X here winds up being bar and beer, and the Y winds up just being beer. Okay, and that is a proper subset of X. Okay, so the result though, the result equals, let's say T of Z, so Z's, and Z equals X minus Y. Okay, so Z is just a set of attributes that are in X but are not in Y. So basically what that means, it means that what comes out of this thing is going to be bar here, because bar and beer minus beer is equal just to bar, right? And that's what you get out. So this is kind of the structure of what's coming in and out. And this can get very, very tricky. And there are a lot of traps with this, but that's kind of what, it's important to kind of keep this in mind as in terms of kind of what goes into a division. So if you feed anything else into the division that doesn't respect this, or you expect stuff coming out that doesn't respect this, then it's going to be easy to mark it wrong, okay, because it will be wrong, right? So just keep that in mind. All right, so now division itself is just syntactic sugars. Now I'm not going to go into this. We're going to go into this later, but by the time the course, okay, basically I'm saying here, if you understand this, then you are on the way to fully mastering relational algebra. All right, so this is the actual definition of what division is actually doing, right? And this actually relates a little bit to that double negation, rephrasing I was talking about before, right? So don't worry about this so much right now. Just, but if you want to kind of, if you want to say I want to get this thing, fully mastered, then go in and figure out why this works here. I'll describe it later, but at this point here, I want to kind of go on to other stuff based on time, all right, and timing. So this is the actual definition of what division is. All right. So again, if you understand this, you are well on the way. All right. Okay. So yeah. So this I think I touched on before, where basically you can when you show these relational algebra expressions, these expressions in relational algebra, You can do them as a program, a sequence of assignments. You can do it, or you can do it as an expression with several kind of operators and operands, kind of just everything building up as one giant expression. You can also express it as a tree. And in fact, as a tree is how the computer is doing it. So the computer, we'll get to this a little bit later, but basically internally inside the representation and in databases, they represent these things as trees. So generally students won't be representing as trees because it's kind of implicit if you just do it as a program or as you do it as a full expression. All right, so yeah, there's some precedents here that you could talk about, but a lot of times you can just deal with the precedents by just boxing things with parentheses. Okay, so expressions as trees. Okay, so this would be as a tree. So you could envision it as a tree here. And this right here, what is this getting us? This is getting us the bars on Maple Street, the names of those bars, and union those with the name of the bar, that the price that basically is going over sell. So the bar is selling bud for less than $3, and we're getting the bars that do that. And then we're renaming it so that we have union compatibility here. So we want to have name here, okay? And then over here, we're also getting the bars on Maple Street. So what this expresses here is the bars on Maple Street, or those that are selling bud for less than $3. All right, now self-joins is something that will come up. So you're going to see a lot of this in your recitation here. So basically, we'd say something like this: find the bars that sell two different beers at the same price. All right, so this is going to require a self-join. So we're going to have to join S with cells with cells, because we're going to be looking for the same. We're going to do a join, so we're basically talking about the same bar, but then we want two distinct beers, but we want to see them for the same price. All right, so how do we do that? We do it the following way. Okay, this is kind of a simple renaming here. So we are going to rename. We're going to wind up renaming cells to S instead, with bar and then beer one. We have beer one here. This was just beer. And so then we have beer not equal to beer one. So you can probably verify how this works. I mean, we can think of this another way. I would do this a little bit slightly different. I can do this as a program here. Let's just do this one as a program, because this will be kind of I think will clear up things. All right. Control all. So if we have, darn it, delete. Good. All right. So let's just do this. So if I have, basically, I'll say this. I'll do it as a program. S. That sucks. S. Bars as a bar. Beer price equals cells. Okay, so now we're making a copy of cells into this new S table, and then we're going to basically say what? We're going to basically take that and we're going to say S. Let's just do it kind of an elementary way. S. Okay, I'll do it the way that they did it on the. I'll say beer one. All right, so that's going to be called beer one price. So basically, what I'll do here now, if I do this, if I do a natural join with cells, what this is going to give us is this is going to give us something like the following. Let's call it T, and it's going to have bar, and it's going to have beer. It's going to have beer one, and it's going to have price. Okay, so notice here when we did the natural join between this and S and cells, it forced equality on all of the attributes, bar and price. Okay, it forced equality on those. But it then, since this was a different name, beer one, we have bar, beer one, and price. So these are all these beer and beer one are going to then by definition have the same price, right? And then all we do then is we basically just say, where does beer not equal? Where does beer not equal beer one, right? So that we don't have, it's not like, because the join will give us stuff where we're going to have like some bar, Joe's bar, Bud, and then the price. That will come in here. So we then need to do this. We need to have a select here. Okay, there we have this, and then let's just say here, result, and then it's called bar. Over select beer not equal to beer one, and then that's going to be over T. Okay, so that'll give us the bars that are selling two distinct beers for the same price. Okay, good. So, all right. So yeah, so this is the union compatibility issue that I talked about before. Okay, so now let's revisit this right here, because we want to talk about tuple calculus very, very quickly. We want to talk about this tuple calculus. All right, so we've covered the relational algebra. You have the ingredients now to do all the relational algebra problems in recitation. Okay, but let's talk a little bit about the tuple calculus. So when we go back to this right here, we said that, well, we want the names. We have company and we have supplies, and then we want the names of the companies in Sweden that have suppliers from China. So this right here, this is an expression in the tuple calculus, all right? And then this will translate down into an expression, and we're not going to do that. We're not going to show the translation algorithm, but there is one. They can always take an expression like this and translate it into relational algebra. Okay, so it's actually not that trivial. It's a little bit tricky, but you can always do that. You can always take an expression like this, and then you can expand it out and generate relational algebra, right? That does the exact same thing. You can also go in the reverse direction if you want. Okay, so so then what is this tuple calculus? All right, so tuple calculus itself, and I'll just kind of go through examples here. Tuple calculus itself is just basically, it's like a syntactic sugar over first order logic. Okay, so the tuples are the variables now. So there's a slight difference between first order logic, or domain tuple calculus is what they call it also. First order logic and tuple calculus, in just the fact that first order logic, let me show you an example of first order logic here. So first order logic would be something like this. Control A. Delete. Here. Let's just talk about like maybe companies with names and countries. ID, name, and country. So if I say this, if I say there exists X, there exists Y, and there exists Z, company X, Y, Z. All right, so that, now usually what I do is I put these here just to kind of make it clear. This right here, this is an expression, all right? This is an expression in first order logic, because you have the variables here, and the variables are ranging over places in relations. So this is really the fundamental first order logic. Now let's do this, let's show the same thing in tuple calculus. The same thing in tuple calculus would be this. There exists X, company X. Okay, so what's happening here then is that we have the same name of a relation, and this relation has three components. It has three attributes, all right? But what we're allowing here is we're allowing for basically this X here is a tuple variable, and it's basically, it's basically pointing to one particular tuple in this relation. So I could say something like this. I could say, up here we have this, and I could say something like X equals IBM. Okay, so that's that expression there. So strictly speaking, I'm going to do it that way. All right, and the way I would do the same thing here is, and this is an and X dot name equals IBM. Okay. So these are basically equivalent. All right. I hope that makes sense to people. So then the question might be, well, why do we even do this? I mean, first order logic is kind of, well established and all that. Why are we fiddling around with this new syntactic sugar? It's kind of like, what's the point? Well, the point is that it's a lot easier to work with. It's a lot, especially if you get a lot of attributes here. If you get like wind up having like 10 attributes in a relation, which is not unheard of, it's a lot more convenient to do it this way with the dot operator. Okay, it's a lot easier. So, but again, I mean, some people in the research community, they basically say, screw this, this is old. But the thing is, it actually is quite useful to have the tuple calculus. It's a nice syntax to actually have. So, Cod, when he developed that, it was a good reason why he did that. Okay, so let's go on a little bit more about what the actual syntax of the thing is, so we can kind of develop some examples here. All right. Control A, and then delete. All right. So, yeah, we have tuple variables, yeah, and then we have each tuple variable is a type, okay, has a type. Then they get access through the dot operators. And then we have the quantifiers, there exist, and for all, the upside down A, and then the standard connectors. Okay, so let's see here. So you get something like this. So what you have is the actual queries, what they have is they have like a variable and using the dot notation, they pluck out some attribute. And then you have such that, that's what this thing's always read as such that, and then you have the formula. All right. And the formula is, yeah, I mean, the formula is open. It has open variable. So it's not a sentence. Remember, if you recall from logic, a sentence is a formula that has no, that all the variables are quantified. In this case, there will be open variables, and we'll show that in a second. So, okay, so let's just maybe do some okay, this I already said. So there's a theorem that says the expressive power of tuple calculus and relational algebra are the same. Okay. All right, so I'll get to that in the very end. So how much time do we have here? Good, we have some time to do this. All right, so let's just do some of these by example. Okay, so let's go back and let's just think here. I want to get the companies in Sweden. All right, so here's the tuple calculus expression to give me the companies in Sweden. All right, so it's going to be a query. So I'm starting out with these kind of these brackets here. And then I'm going to basically say this. I'm going to say, I want the names, x.name, all right, such that. Okay, so this is the name. Yeah, okay. So now, all right, let's look at this one here. So I'll just put this down here. Okay, so there's a query. So what is this going to do? This is just going to give us the names of all. This is like a projection. This is like projection on name over the table company. All right. But I said that I promised to get the ones in Sweden. So and x dot country equals Sweden. Okay, so what does this say? This says basically, remember, this would basically get translated into relational algebra, right? When we want to evaluate it. It's a little difficult to see. Can you guys see the whole thing? You guys can see it, it's just hard to read, right? Is that what you mean? It's like, yeah. Yeah, I'm going to try to kind of figure out, I'm using Google Draw here. I'm going to try to, I mean, yeah, anyways, I'm trying my best. It was the one before. Yeah. Okay. I mean, it's okay, but it's not ideal. I realize that. Okay. So anyways, so those are the companies in Sweden. All right. So now let's say we want to have the companies in Sweden that they have somebody supplying to them. All right. So I mean, it might be all of them, but let's do that. All right. So if we want to do that, then we do the following. We say and. Okay. Here. There exists y. All right, so I'm saying there exists a y, and then I'm going to say something about that y. So everything down here is going to be what we're talking about, that y. All right, so the y is a supplies. All right, so it's a supplies tuple. That's what it is. And x.id equals Y supplies. Or I should maybe say, what did I have in the supplies from, sorry. Okay. So now I do this. All right, so what do I want to say? I wanted to get the countries in Sweden who have a supplier. So someone supplies to them, okay? So that means it would be basically that this two, okay? So there's a record of supply that's going into X, all right? Does that make sense? Does everybody follow this? So this is a use of the existential quantifier. All right, so now what does this look like in relational algebra? Yeah, I mean, it looks like there's going to be some kind of join, right? Yeah, I mean, I mean, writing a general translator is not super trivial, but you have to take it on faith that you can. I mean, certainly if I ask you, could you give me the doing relational algebra? Please give me the names of the companies in Sweden who have a supplier. Can you do that in relational algebra? Okay, well, the answer is yes, and you'll do that kind of stuff for recitation. All right, so let's see, how much time do we have here? I think we got enough time to do it. Let's do a little bit of a trickier one, and let's do the one where basically we want to get the names of the well, let's do the following. Let's do the one where we want to get the names of the well, okay, let's just take it all. Let's just do the whole thing. We want to get the names of the companies that supply every company in Sweden. All right. Okay. So how are we going to do that? We want the names of the companies that supply every company in Sweden. Let's do it the following way with the universal quantifier. So this will show us kind of how the universal quantifier works. I'm going to try to. Okay, so we have company and we have supplies. Okay, so does everybody understand what we're after here? We're after the companies that supply every company in Sweden. Okay, so let's just do this. Control A and then delete. All right, so taking it from the top here, because this will be a little bit longer. All right, so I'm going to basically say this. Give me X name. Okay. All right. And then I'm going to say that it's going to have to be a company. Okay. All right. That's not so pretty, but okay. So now that's the names of all the companies, but I want the companies that supply all the companies in Sweden. So, and all right. So let's okay. Now here's what we're going to do. We're going to say for all Y. Okay. For all Y. If Y is a company and Y dot country equals, okay, that's Sweden. Okay. Yeah. Well, one sec. We're going to do it. If we get the time, we're going to do the one that uses existential quantifiers as well. But let's just stick with this one right here, because I think this is maybe a little more straightforward. So listen, for all the companies where their company is in Sweden, that implies there exists a record. All right. And this is supplies. All right, maybe I have time, this space here. All right, so for every company in Sweden, there exists a record of supply where Z dot from equals x dot id, right? And z dot 2 equals y dot id. Okay? That, and that. That matches this one. Oh, and then we have to have this. Okay, that's the this guy right here matches this guy right here. Okay, so let's try to figure this out. What are the, so I mean this looks pretty sloppy doppy. Sorry about that. Let me just try to see if I can clean this thing up somehow. All right, does everybody realize? Okay, that's x dot name. This is this open squiggly, and that's a closed squiggly. Everybody's got that, right? This is an open parenthesis. There's a closed parenthesis. This is an open parenthesis. There's a closed parenthesis. All right. This is an and. That's an and. That's an and. This right here, this sorry specimen here, is z dot from. Okay. And this is x dot id. Got it? Hope. And this sorry specimen here is z dot 2, and this is y dot id. All right? Okay, so what is this really saying here? All right, so what this is saying is it's saying that so let's think this thing through here. All right, so I have a company, right? I grab a company. I grab this one company called, let's say, Microsoft, right? Now I ask myself the following question. Is it true that for all the companies in Sweden, that there exists a record of supply that the record of supply is from Microsoft, because the from is equal to the ID of, I said X is now clamped to Microsoft. This record of supply also says, because we're just looking for one that exists, this record of supply also says that it's to the company in question. Right? Then let's say just hypothetically that all the companies in Sweden are, that Microsoft supplies every company in Sweden. All right. Then what that would mean is it would mean that, yeah, as you range over the companies in Sweden, as you range over all the companies in Sweden here, you would find a record of supply from Microsoft to that company. Is that clear? All right. So that's kind of what that's what this thing is expressing. All right. Now, if you want to get into it, is this expressing the same thing? That's a double knot there. Yeah, it should, because double knot, I mean, I can just add a double knot. That's not a problem. Right. So what happens when this knot interacts with this for all right here? So there's basically, what this actually says here is this, if you do this, if you apply this here, what this will wind up doing. So if I basically say this, I say not for all P is equivalent to there exists not P. Okay, those are equivalent. This right here is a way that you can kind of transform. You can wind up pushing this negation through the quantifier. In the process of that, what you'll wind up doing is you'll flip this to a okay, so we're going to flip that to an exists. Okay, so this not hopped in here. It flipped this to an exist. It's too bad I need an eraser, little eraser widget or something. And then the negation lines up here. All right, so we have so it's not there exists y, and then not this whole thing here. So now, if you get used, I don't think I'm going to go through the whole thing this lecture, but basically what this thing does is this is going to hop in here, and it's going to flip all these and put negations here. Okay. This right here actually should have been, this is just this or that. So there's all the logical equivalence you can do. And at the end of all this, if you push all these things through, you'll wind up getting the following. You wind up getting the following expression. One second. Control A. And then delete. You'll wind up getting the expression. All right. you get the, you'll essentially get this expression that says not exists y where company y dot country equals, this is terrible, Sweden, and there does not exist a z where supplies z and z dot from equals x dot id and z dot to equals y dot id. All right, so you have to take it on faith here that if you push this thing through, if you push through those manipulations or those kind of flippings of the quantifiers, you'll wind up getting an expression like this. And then what this says is, it says, give me the companies where there does not exist a company in Sweden for which there does not exist a record of that company supplying the company in Sweden. Right? So that's kind of the relation it has to the double negation. So it shows that you can always kind of transform the for alls into not exists. And we'll see ultimately that SQL uses that because SQL will only have a not exists and an exists rather than having for all. So there is no for all in SQL because you don't need it. Right, and this is kind of showing a little bit why you don't need it. Now, there's some other issues I want to talk about a little bit about what the semantics really are of universal quantification, but we'll come to that a little bit later as we develop things. All right, so good. Okay, so let's see here. So I think we have some time here for this. Yeah. So all right. So this was a kind of a crash course in the tuple calculus. Now, when we get to a little bit more realistic picture, so there was the idealized picture I had before where at the very top here, we have tuple calculus, and then we have relational algebra, and then we have maybe an equivalent relational algebra. This is actually the more realistic picture of what's going on in SQL systems. So what's going on in SQL systems is we're not using tuple calculus, we're using SQL, right? Which is kind of like the tuple calculus. And then we're not using relational algebra. We're using rather something called extended relational algebra, but it's very much like the relational algebra. So this relational algebra stuff is being implemented in databases. It's there, but it's extended and for a lot of practical reasons. And then the optimization is basically an equivalent extended relational algebra expression that can be executed more efficiently. Okay, so the key thing here is that when the first move we're going to make toward getting a little bit more realistic picture, something a little bit more useful, is we're going to go to bag semantics. So bags, or multi-sets if you want to be more mathematical. Bags is like a set, but then you can have elements that are repeating, right? So SQL is based on the bag semantics, right? So, and so is extended relational algebra. So all that stuff I was saying before about how, if there are duplicates, get rid of them, that's true automatically under set semantics. But now we're just going to be lazy and we're not going to get rid of duplicates, right? And there's a lot of benefits to being lazy because you don't have to do the computation, right? So that's just consider that once I say we're going to bag semantics, now we're taking more of a realistic turn. Okay, so why bags? Yeah, so some operations are more efficient, like projection under bags than sets, because when you do projection, you don't have to track. If you're doing bags, all you have to do is just kind of run through the relation, marking things, not checking for duplicates. All right, so selection applies to each tuple, but it allows for duplicates to be in the result. So all the relations now are bags rather than sets. Okay, let's see. Can you say that everything can be a bag but not a set? Not really sure. Strictly speaking, a bag is, sets remove duplicates by definition. That's kind of the way they work. All right, a bag. I mean, what we'll see is there are operations in SQL, so you can actually apply. You can get back to the set semantics, so you can remove duplicates. So if you want to make sure that your SQL is only is operating only under a set semantics, you can force it. All right. So for those who want to stay with set semantics, one can absolutely, but just the SQL by default is it's not even by default. The SQL by definition is doing the bag semantics. To turn all your bags into sets, you have to have explicit operations inside of SQL to do that. Okay, good. Yeah, I mean, this is not so complicated. It's just, but it's important for us to get the terms right because they are distinct things. All right, so selection applies to each. Okay, so projection then also doesn't eliminate duplicates, and so duplicates. Yeah, okay. So bag selection here. This is just some examples of it. So yeah, so this is a bag. This relation here is a bag because we already have a duplicate, and then there we are also getting back a bag. Likewise, we have one being repeated here. Bag product. Yeah. So bag products. Yeah, I mean they really do all the. I mean, it's kind of what you would expect. So if you have 3 tuples here and you have 2 tuples here, how many are going to get in the result? It's the same old thing with the Cartesian product. You're going to get 3 times 2, 6. All right, theta join. Yeah, so this is bag union. Okay, so bag union is kind of interesting. So bag union is it tends to allow for duplicates to kind of as you do the unions, duplicates just wind up being tagged along. So it's not idempotency. So the idea that S union S. So normally under set semantics, S relation R, say union R equals R, right? It's idempotent. But in the case of bag union, it's not the case because it'll just keep on repeating stuff. And then intersection is kind of tricky because intersection winds up doing like a little bit of like you calculate the number of matchings and then that's what's left over. So you have, in this case, you have 3 ones on one side and you have 2 ones on the other side. So you only get 2 ones in the intersection on the bag. That in itself kind of can make things kind of so this would complicate things. So theoreticians don't like bag semantics. So when you talk about the people, so there's a lot of, like I was talking about before, when I talked about, if you're into theory, you can work with relational databases. But generally speaking, the theoreticians like to stick with set semantics because there's a lot of nice properties. It gets pretty grubby when you do okay. And likewise with difference, it's kind of a counting down here. So this one here knocks out one of the ones, but not the other one. So there's 2 ones here. So yes, clearly bags laws do not equal set laws. So there's a lot of some of them hold, like commutativity for union holds, but other ones like idempotency, they don't. So here's an example of idempotency. It doesn't work for bags. So okay, so what did we cover? We covered the relational algebra. We covered the tuple calculus. We talked about set semantics. And we talked about bag semantics. I think you guys have enough ingredients to do the recitation 1, which is going to be released shortly. So, okay, so that was that. Are there any questions, or shall we just conclude here? And I'll post this this video after it saves. Okay, so let me see. I'll just stop share here, and I'll stop the recording. Okay, pause, stop recording. Is the tutoring in the afternoon on this Zoom link? No, that's the tutoring is for the lab. So that's going to be class. Class is going to run that whole thing. But since you guys haven't got any labs yet, then it's still, it's still kind of, it's not really. I'm not really sure exactly when, but fairly soon lab 1 will be released. I kind of want to cover SQL. I think I'm going to cover SQL in the next lecture. So once we have that, excuse me, once we have that kind of out, then we'll put out the lab 1. But I think lab 0 is out. So lab 0 is just a warm up. Okay, true. Oh, I think it's on. Yeah, yeah. Class is going to be using that queue, so that should be. Yeah, well, I mean, there's no rush on this right now because labs haven't been released, but this will all be clear. All right. So any other questions? No, there's no afternoon today. I don't think there is anymore. There was when he first did it under time edit. He added those, but I think those have been taken. I think it was taken away. I hope it was. So yeah, there's nothing this afternoon. I mean, what we'll have this afternoon is you'll have, if you want to stay busy, you're going to get recitation 1 this afternoon. Oh, so maybe class is going to do something. I'm sorry that there's a little bit of confusion here. I can ask class about it. Okay, so he decided he wanted to. Yeah, you got to follow the link. So there's info about it. Okay, I see. Yeah, all right. Yeah, everything's on Cambro. Can you go to web apps? Okay, so it looks like you guys are communicating among yourselves about what how to get to get this worked out. So. Are there any more questions? Okay, I mean, I'll send out an email to the. By the way, how many people got my email, my introductory email? Did anybody not get it? I'm assuming that Cambro is getting up to date. I'll send out once recitation 1 is released. I'll send out an email. So if you don't get an email this afternoon, but then you go and you see that recitation 1 has been released, then you're not getting email. So we'll get that solved. And also just a general thing, I just want to everybody understand that as far as like administrative stuff, like if you show up for the class, and if somehow you're not registered or whatever, and time goes on, it's like you're not going to get. I'm always like open. I mean, I never like play little games. Well, you didn't make it within this particular. I mean, I'm not that kind of person. I always tend to favor in terms of like we can work things out, we can straighten it out, and get you in. So, but that's not to say that you shouldn't start. I mean, it's good to kind of get things straight, but don't stress about those kind of administrative things. There's no gotcha with that kind of stuff for me. Okay, then. All right, great. So anyways, we will all see each other next Monday. Okay, all right, bye-bye.